Hello everyone, I'm Ronapi Chai-Chawarat from International School of Engineering, Chulalongkorn University. So our today topic is passive knee exoskeleton using brake torque to assist stair ascent. Passive exo are usually more compact, robust, and less expensive than power exo because we don't have a huge additional energy source in the system. And yeah, without the high power actuator, the assistive performance is inferior to power exo and also highly dependent to the motion pattern. We should carefully decide the strategy to manipulate the energy, when we can store, when we can release the energy to support the motion. Some of passive exo have been developed for the level walking or even running, but none of them focus on the stair ascent or descent. But we have a lot of research focused on the biomechanics of the stair ascent. If we consider the knee angle, which is the angle between the upper leg and lower leg, during the stair ascent, when we begin the cycle from the stand phase, when the foot touch with the stair, we flex the knee with a big angle, and then when we kick ourselves up the stair, the knee angle decreases, and we flex the knee again in the swing phase. About the knee moment also vary in the cycle. We propose one idea to indicate whether the knee moment is flexion or extension moment by consider the ground reaction force. If the ground reaction force is anterior to the center of rotation, we can assume that we may require the flexion moment so that the lower leg part is in the equilibrium of the moment about the center of rotation. And yeah, we may require the knee extension moment when the ground reaction force is posterior to the center of rotation, which makes sense, right? In the early of the stand phase, we require the flexion moment, which is a positive moment in the moment plot. And in the latter of the stand phase, the extension moment is required. And yeah, we still have some advantage of the stair ascent as we compare to the level walking. The first advantage is that we require the flexion moment during the continuous extension of the knee, and the angle that change during the stand phase of the stair ascent is big range. In this plot, maybe from 50 to 0 degree. But in the level walking, the angle may change maybe between 0 to 20 degree, and like in the small range. The stair ascent has advantage in terms of the angle sensitivity because we can have a big range of the angle to use the same sensor to sense the change of the angle and apply the supporting strategy on which angle, how much torque we can support the motion. But what kind of actuator can provide the flexion moment during the knee is extending? So our idea is to use the brake, which is the negative energy source or a kind of energy dissipator. If we consider the working condition of the brake, it can work only when the knee moment is required in the opposite direction to the angular velocity. In our case, for example, the brake can be used when the knee is extending, but we require the flexion moment, or when the knee is flexing, but we require the extension moment. So we assume the assumption that no human robot interfacing loss, which means that the original knee moment can directly be subtract with the supporting knee moment by the brake, so that we can estimate the resultant knee moment as the dashed line. But in the real application, we may have some effect of the interfacing loss. But yeah, this is just show in the concept. And one more thing that we consider in this research is we know that in the stair ascent application, the knee angle change in a big range, and also the center rotation also like change a lot along its trajectory. And we apply the idea of the crossing four-bar knee joint for the exo so that it can follow and have the kinematic compatibility with the human knee joint during flexing with a big angle. And we can put the brake on the pin A, B, C, or D, but it's not easy to put the brake on the center of rotation on the point O. In our case, we put the brake at the point D, and we derive the relationship between the torque around the point O that is generated by the brake that put at the point D. And if we have the constant brake torque, the real torque about the point O is lower than the constant brake torque. And in our case, we plan to use the brake to support between the knee angle from 20 degrees to 48 degrees. So we have slightly lower of the magnitude of the brake moment about the knee joint as compared to the constant brake torque that we apply at the point D. We built the Exo prototype, and yeah, it made from the 3D print part, and we use the electromagnetic brake and control it with Arduino and use the 8-bit motor driver. And we also have the encoder to measure the rotation of the pin and relate to the knee angle, because in our application, we need the knee angle information because the brake torque will be provided between the range of the knee angle. And we also have the manually push button so that the user in the experiment, he need to put a signal to indicate the starting time of the cycle. And the Exo will notice this and support the brake torque in the stand phase only. And for the electromagnetic brake, we perform a static test to find the relationship between the torque and the applied voltage. And we can observe the linear relationship between the brake torque and the applied voltage. And in the test, we have a healthy male participant wearing the exoskeleton on his right leg, and we put the EMG sensor on the rectus femoris on the front of the leg and the bicep femoris on the back of the leg. And the participant walked up the stair continuously, and he put the push button to indicate the start timing of each cycle. And the Exo will support only the odd cycle, which means in the first, third, and fifth cycle, the Exo will support. On the second and fourth cycle, the Exo won't do anything and let the participant to walk freely so that we can compare the result with and without the Exo. And when we check the EMG result of the rectus femoris and bicep femoris muscle, we found that, yeah, rectus femoris muscle, the activity is high in the early of the stand phase. And bicep femoris muscle, which relate to the hip extension and knee flexion moment of the knee, and the activity will have 3 peaks in a cycle. And with the Exo, we found that we can reduce the muscle activity in the first peak of the rectus femoris, and we also see the possibility to reduce the second peak of the bicep femoris muscle activity. By the way, with this prototype, we need to have the reliable phase detection method, because with the current test system, the participant need to press the button every time he put his right leg on the floor. And we need to control the speed of the walking up the stair to compare the muscle activity. And we plan to test with multiple participants, and also plan to analyze the result of the knee angle to check whether the brake support affect the knee angle or not. And for future study, for the improvement, we may need a brake with a higher torque, but more compact size. And we also see the possibility to extend the concept of the brake support for the stair ascent also. So thank you very much, and welcome for the question.